Welcome to part 4 of my 8-part series on science and the Bible. I strongly suggest that you listen to the parts in sequence. Enjoy.
Okay, I'm going to read you a section on this bird you're looking at on the screen. It's called the incubator bird or the brush turkey. It's from Australia. This is from Joe Martin's book, The Evolution of a Creationist. The megapode or incubator bird of Australia is unique among birds. This 3 to 4 pound bird resembles a chicken or a small turkey. Some native Australians call it the brush turkey. The incubator birds are unlike all other birds. So if they evolved, from what did they evolve? Or what are they evolving into? An article in Scientific American offers precious little by way of an evolutionary explanation for the origins of this strange bird. All birds use body heat to incubate their eggs, except the incubator bird. Now here's a quote from a scientific journal. Instead, they pile up great heaps of debris which serve as incubators. The warmth of the fermenting compost does the work. In one species, the scrub fowl, a mount 20 feet high and 50 feet wide, has been reported. Instead of using its own body heat to incubate its eggs, as does the chicken who sits on her own eggs, the incubator bird uses fermentation heat and, quote from another article, some solar heat and others use the heat produced by volcanic action. A bird that uses volcanic heat or the warmth of a fermenting plant to hatch its eggs? Incredible. If there are any creatures that could not possibly evolve, the Australian incubator bird joins the bombardier beetle as such a creature. The female is responsible for 2 activities. First, she must test the nest to be sure it is adequate for incubating her eggs. What explanation can evolution offer for the ability of the hen to evaluate the suitability of a nest that may be dug 3 feet into the earth and extend 15 feet or more above ground and up to 50 feet across? And what would motivate a little 3.5 pound male bird to get busy constructing monstrous nest number 2 should the hen reject his first effort, which apparently they do sometimes? After accepting the nest, the second responsibility of the female is performed. She lays 20 to 35 eggs at the rate of 1 egg every 3 days for up to 7 months. As many as 16 eggs can exist in a normal mound at any one time. Each egg weighs about ½ pound and is about as large as an ostrich egg. That's a tremendous amount of work for a 3 to 4 pound hen. Can you imagine getting an egg the size of grapefruit from a 3 pound chicken? No wonder that upon completion of her laying task, she leaves the nest never to return. She takes no part in the incubation or raising of her chicks. This is not your normal evolutionary way. At this point, the male begins to perform his God-given job of managing the incubation of the deeply buried eggs. For this species of incubator chicks to survive, they demand a precise temperature of 91 degrees Fahrenheit. Yes, exactly 91 degrees Fahrenheit. If the male bird wants the chicks to survive, he will not let the temperature vary more than 1 or 2 degrees on either side of 91 degrees Fahrenheit. How does the daddy bird maintain a consistent temperature of 91 Fahrenheit in a mound of decaying plants and dirt? Scientists differ on the mechanism they think the bird uses to measure the temperature. Some think the bird's thermometer is in its beak. Others believe the tongue can distinguish 91 degrees Fahrenheit and a few tenths of a percent above and below 91 degrees Fahrenheit. Here's the point. How could a bird evolve the ability to precisely measure temperatures with its beak or tongue? Evolution has no credible answer. How would the incubator bird know it needed to keep its eggs at exactly 91.5 degrees Fahrenheit, or 91 degrees Fahrenheit? The chicks would get too hot or too cold and die before he figured it out. And dead creatures do not evolve into higher forms. You may be asking, well, how does the bird keep those eggs at 91 degrees Fahrenheit? The male digs down into the nest and checks the temperature. On hot days, he may pile extra sand on top of the mound to shield it from the sun. He may even rearrange an entire pile of rotting leaves and grasses several times a day. On cooler days, the male megapodes, which the name means big feet, will push material off the top of the nest to permit more sunlight to penetrate the decaying organic material. Or to keep the humidity at 99.5% around the eggs. He may dig conical holes toward the eggs to get more moisture deep into the nest. Keeping temperature and humidity just right is a big job. Concerning the precision needed for incubation temperature maintenance, a scientist, Seymour, writes, the process is very precise. 1 centimeter of fresh material added to the mound can increase the temperature by 1.5 degrees C. That's enough to push it out of the range and cause the eggs to die. Not only must the eggs be kept at 91 Fahrenheit and 99.5% humidity, but the chick must get enough air to breathe. The father provides the fresh air for the chicks as he daily digs down to the eggs. But the chick must get the air inside the shell. This means to get air inside the shell was provided by the hen as she formed the shell. It has thousands of tiny holes called pores in it. These holes in the thick shell are shaped like conical ice cream cones with the narrowest part of the cone toward the chick. As the chick grows, it cannot get enough air through the bottom of the cone, so it begins to move the inside layer of the shell. As he thins out the shell, the holes get bigger as he moves up the cone, and the chick can get more air. Amazing. There's more to it, okay? But let me show you some photos, okay? Here is a real incubator bird. Here is a schematic of its pile. And remember, this thing can be 50 feet across. Right? That's 15 meters. And the eggs are buried quite deep. All right, now I'll show you a picture of one in a zoo sitting on its nest. It's pretty impressive, isn't it? This is the male, by the way. Mama has flown away, never to come back. You know, if you remember Horton hatches the egg, it's Daisy May. I don't know if you remember that. Anyway, this is quite fascinating, and it's very hard to explain from an evolutionary viewpoint. We haven't gotten to evolution yet, but these things are fascinating. Okay, I'm going to take that down, and we're going to go back to our discussion of origins and processes. Okay, now we're going to move on to laws of physical process. Now, I think, has the offering been taken up? It's in process? Okay, good. All right, laws of physical processes. Whoops, wrong button. I'm back. Okay. Now, it's true that our primary goal is to understand origins, but processes are very important too. They give us a tool to look back in time, or more accurately, to think back through time. Okay? Now, the two most fundamental laws of physical processes were discovered in the study of the behavior of steam engines. This led to what's called the science of thermodynamics. Now, remember last week we were talking about the Industrial Revolution and the Scientific Revolution? Well, I believe it was in the late 1700s that people began to use steam power. Steam power was developed largely in England, and one of the ways in which it was developed very early on was to help in coal mines. Coal was used very much in England as a source of energy, and in order to get coal, you typically have to dig very deep underground. Now, one of the problems with coal mines is that they fill up with water. Rainwater comes down, and there are cracks in the earth, and they just fill up with rainwater, and it's very easy for miners to drown. So people who operated mines had to have pumps to remove that water. Now, in the early days, those pumps were powered by horses walking around in circles. And by the way, that's why the power of engines is measured in horsepower. Well, in the late 1700s, a number of people began to realize that you could use steam to generate power. Now, the early steam engines were kind of interesting. Modern steam engines put highly pressurized steam into a piston, and the pressure pushes the piston. But the earliest steam engines didn't work that way. They would start with a piston that just had regular air in it. They would inject hot steam into it, and then they would throw cold water on the sides of the cylinder. The cold water would cause the temperature of the steam to drop. The pressure in the cylinder would go down, and air pressure would push the cylinder down. So they actually were sort of like vacuum engines. That was good. Eventually people learned to make pressure-operated engines. Now, in the process of trying to make more and more efficient engines, people discovered something. And you all understand what efficiency is, right? We talk about cars, we talk about kilometers per liter or miles per gallon. Well, they wanted to get as much work out of a given amount of coal that was used to operate the steam engine as possible. And there was a lot of improvement made over the years, but they reached a point where they could not make the engines any better. And scientists began studying this, and they discovered what we call the laws of thermodynamics. They discovered that with any heat engine operating in a certain temperature range, like the temperature ranges are determined by the highest temperature of the steam and the temperature of the air and the environment around, right? When those temperatures are far apart, you can get a pretty efficient machine, but you can never get 100% efficiency, no matter how far apart those temperatures are. In the process of this study, they discovered what we call the laws of thermodynamics. Now, these laws are very, very important, and they turn out to apply to a lot more than just thermodynamics. I'm calling these the unavoidable constraint. Okay? The most fundamental laws of physical processes are the two first laws of thermodynamics. Now, the first law of thermodynamics says that mass energy. Now, for the moment, just pretend the word mass isn't there. I'll explain why it's there in a few moments, okay? Let's just say it that way. Can you hear me? Okay, I don't know what's happening with the mic. All right, energy is always conserved. It can neither be created nor destroyed. The total amount of energy in any closed system, including the universe as a whole, is a constant. Now, let me tell you why I said mass energy here. When this law was first formulated, people did not know about the possibility of converting energy into mass and mass into energy. That was developed in the early 1900s, and it was first exploited in the atom bomb. You all know about nuclear power, right? But Einstein's equation, E equals mc squared, energy equals mass times the velocity of light squared, basically tells us the conversion factor. If you take this amount of mass and you convert it into energy, you'll get that amount of energy. If you take this amount of energy and convert it into mass, you'll get that amount of mass. Now, by the way, you can create gold from energy. Do you know that? You can. You can create mass from energy. Now, if somebody ever comes to you and wants to sell you a machine, and he said, just plug this into your wall, and it will use the energy of electricity to make gold for you, don't buy it. Now, it's possible it could work. It would be a very sophisticated machine. Today, it takes a particle accelerator, the size of half of Hong Kong, to turn energy into mass. They do it. The problem is, the amount of energy it would take to produce any measurable amount of gold that would be good to you would cost far more than the gold would. Okay? But you can turn mass into energy, you can turn energy into mass. But the combination is always conserved. Right? Now, the second law of thermodynamics says that in any physical process, something called entropy, I'll explain what entropy is in a few moments, will either increase or remain the same. Now, another way to say that is that in any process, available useful energy, order, or information will either be conserved or lost, but never gained. Right? Now, The first one is the first law, and you can put it this way. You can't get something from nothing, there is no free lunch. Okay? The second law can be put this way. You either lose or you break even, everything decays and runs down. Now, by the way, this also describes long-term gambling. You know, the house always wins, right? You can't become rich by gambling over and over and over and over and just continuing, because you will steadily lose. Sometimes you'll win, but you'll have a net loss. Now, this law says you'll never even have a temporary win as far as entropy is concerned. We'll explain that in a few moments. Okay? Now, this was the law that was particularly important to steam engines. I mean, this one obviously applies. If you don't burn coal, your steam engine isn't going to run. But this law says that no matter how well you build your steam engine, you can only get a certain amount of useful energy out of that coal. Right? Let's say you put in, let's use joules as the measurement of energy. Let's say you put in 100 joules of energy in a very well-designed steam engine, operating in a place where the ambient temperature is 20 degrees C. You might have a steam engine that will turn 60% of that energy into useful work. The rest of it is going to go away in waste heat, and there's no way to turn that waste heat into useful work. Now, there's no loss of energy, right? You started with 100 joules, you end with 100 joules, but only 60 joules are turned into useful mechanical energy. The other 40 joules go away into the environment as heat. Okay? Now, let me give you some examples of this law. It's very important that we understand this law. We're going to be talking about entropy, the loss of organization, the loss of information, and the increase of entropy. Okay. Entropy is kind of a weird thing. Entropy is a measure of disorder. Okay? Let's suppose I take this cup and I fill it full of ice cubes and I put it in an extremely well insulated cooler. Let's imagine that I have a cooler that's perfect. No heat can get in and no heat can get out. Right? When I put this cup full of ice cubes into the cooler, there will be air in the cooler that's room temperature. There will be the cup, which probably isn't quite as cold as the ice cubes. And there will be the ice cubes that are very cold. Now, if we put it in there and we wait a long time, what's going to happen? The ice cubes will melt, the temperature of the air will go down, the temperature of the cup will go down, and the temperature of the water that's in the ice cubes will go up. And they will reach a flat point, and if the cooler is perfect, the temperature will never change after that. Now, the first law of thermodynamics would allow the possibility that the ice freezes again and the air gets warm again. But the second law of thermodynamics will not allow that to happen. It will never happen. You will never find ice cubes again, right? Entropy says that things make an effort to move into the least organized state, right? Now, here's another example. You go to the wet market, you buy some nice vegetables, you put them on the counter and you're expecting to chop them up and cook them for dinner. But something happens and you have to leave town suddenly. You come back a week later, what's on the counter? Ugh. Rotten vegetables. Will those vegetables ever unrot? They'll never go back to what they were. They'll never go back to what they were. Flat tire. You're driving down the road and you hear this thump, thump, thump. And you get out of your car and you look and your front tire is going psss. Now, eventually it's going to stop going psss. Now, is that air lost that was in the tire? Is it lost? No, it's in the atmosphere. It was in the tire, now it's in the atmosphere. Okay? Will it ever go back in the tire by itself? No. Now, if you want to think about this in a lot of detail, it took a lot of energy to compress that air into the tire. When the tire was punctured, that air came out with a lot of velocity, right? If you'd held a tissue over it, it would have blown the tissue. Well, that energy goes out into the environment. Some of it will create a tiny wind. Some of it will create heat. Some of it will create noise. None of that energy is lost. That energy is still in the environment. If you want to think big, it's still in the universe. All of those atoms of the air that were in the tire, they're still in the universe. There would be no violation of the conservation of energy if the air pushed its way back through the hole into the tire. Now, are you going to sit around and just wait for the tire to reinflate itself? No. You got to patch it, and you got to spend more energy to pump up that tire, right? Because entropy has increased. When that air leaks out, a system that was very ordered, compressed air inside of a tire, has now become disordered. Okay? Now let's get more technical. In the Philippines, when we lived there, electricity was quite unreliable. And it's hot in the Philippines. So, a lot of people in the Philippines have rechargeable fans. When we first moved there, I would say about 40% of the time there was no electricity. We were living in Manila. And it's hot at night. Now, we had an air conditioner in one of our bedrooms, and the kids and my wife and I would all crowd into that bedroom so we could sleep at night. Well, when the power went up, no air conditioning. We quickly learned that we needed a rechargeable fan. And it's not very powerful, but it's better than nothing. Now imagine that you take a rechargeable fan, and you charge the battery up, and then you put it in a large box. And the box is sealed. It's very strong. It doesn't vibrate. No heat can get out. No heat can get in. You turn the fan on, and you close the lid. Now what's going to happen? Air is going to move around in the fan. The fan is going to run, right? And the battery is going to slowly run down. Now the energy that is stored in the battery is being turned into kinetic energy of motion. And that air is moving around, it's bouncing off the walls, it's turning into heat. Eventually, what you're going to have in the box is a rechargeable fan with a discharged battery and a lot of hot air. All of the energy is still in the box. Now, this is an interesting thing. You may not know this, but most DC motors, if you run them backwards, will recharge the battery that runs them. Did you know that? You could actually charge that fan by driving down the road and holding it out the window and making the wind spin the fan backwards. Well, is all that random motion of air in the box ever going to make that fan spin backwards and recharge the battery? It's never going to happen. Because entropy has increased. Same thing, when you burn wood. There's energy in the wood. There's chemical energy in the wood. When you burn it, it combines with oxygen. Heat is released. It goes out into the environment. CO2 is produced. It goes out into the air. You know, maybe it's the cause of global warming. Maybe it isn't. But it's out there. The heat is out there. Is that pile of ashes ever going to turn back into a piece of wood? Not without effort. Somebody might be able to reassemble that back into a piece of wood if he was really clever. But it would take intelligence and it would take energy. Okay? Now let's talk about entropy in terms of the loss of organization. How many of you have a sock drawer? Some of you have a sock drawer. You keep all your socks in one drawer. Now, I usually organize my sock drawer on the day that my wife washes all the laundry. And the socks are all in there, and they're laid out very nicely, and everything is neat, right? If I do that on Monday, by the end of the week, it's a mess, right? Tipped dominoes, we talked about those before, right? When you knock down that long string of dominoes, was energy lost? No. Was momentum lost? No. We know that energy and momentum are conserved as long as mass isn't being turned into energy. Right? When those dominoes tip over, the momentum of their falling is transferred to the floor and it's transferred to the earth and it makes the earth shake. Right? The energy is still out there. Are those dominoes ever going to stand themselves back up? Now they could, without violating conservation of energy or conservation of momentum. There would be no violation of the first law of thermodynamics. But there would be of the second law, and we know it's not going to happen. Your desktop, whether it's your desktop on your computer or your desktop on your desk. Chinese New Year. Oh, I got to clean this up. 2 weeks later, what does it look like? A mess. Buildings in an earthquake. Now this is a really interesting but sad one. Have you ever seen pictures of places that have been devastated by earthquakes? If you go to that place, there's nothing missing. Everything is still there. All the materials that went into the building, all the possessions, the people who lived in the building, everything is still there. Nothing is lost. But the organization is gone. It's broken up, it's scattered, it's a mess. And I don't care how hard you shake the earth or how well you shake the earth, it's not going to turn back into a building. Now, British people like sugar in their tea. Take a hot cup of tea and a sugar cube. Put it in the tea. What happens? It dissolves. Will it ever turn back into a sugar cube by itself? No. Now, a clever scientist could boil away the water, collect the sugar, recrystallize it, form it into a cube, and get it back, right? But in order to do that, he has to apply intelligence and effort and energy. Okay? Now let's talk about information. Do any of you like to play Scrabble? Okay, a few of you do. I hate Scrabble. I hate board games. I call them B-O-R-E-D games. Right? But my sister-in-law loves to play Scrabble. She plays online with people. She has a magnetic one. They play in the car when they're traveling. Wherever she goes, she's playing Scrabble. Now, if you're playing Scrabble with the kind of board that has the little movable letters, if you're playing and one of the kids runs into the room and bumps the coffee table and all the letters fall off the board, where did that information go? I don't know exactly where it went, but it's gone. Entropy just increased. All right. Does anybody know what DSS stands for? The Dead Sea Scrolls. Okay, the Dead Sea Scrolls were an extraordinarily important find in the 1940s that helped us to have concrete evidence that the Old Testament scriptures that predicted the birth and ministry and death and resurrection of Christ were written long before that happened. Now those scrolls have been very carefully taken apart and read, etc. But there are portions of those scrolls that were destroyed before anybody ever touched them. That information is gone forever. Now, the jar that the scroll was in still contains all the material that was put in the jar when it was sealed. Right? The animal skin or the copper or whatever it was written on, it's still in the jar. The ink is still in the jar. Everything is still in the jar. But the information on the parts that are damaged is lost. Right? This is entropy increasing. How many of you have ever had the hard disk on your laptop crash? How many of you discovered that you didn't have a backup? All right? Very sad. Where did that information go? It's gone. And no matter how long you wait, it's not going to reassemble itself on your hard disk. When I was in high school, we had all kinds of neat shop classes, and one of our shop classes was printing class, and we actually learned how to put together lead movable type. You remember how people used to use lead movable type before what we have today? We'd actually made a little newspaper by setting the letters up one by one, and they had to be backwards. You know, it was really weird. It's hard work to set up just one page. Well, I knocked the tray off the table. And all the type scattered on the floor. And my classmates wanted to kill me. No matter how long you wait, it's not coming back by itself. Did you ever shred a document you shouldn't have shredded? Or did you ever have your financial advisor shred a stock certificate? I hope not, but it would be bad news if it happened, wouldn't it? And I don't care how long you try getting down in that pile of little squares, you're not going to figure out how to put it back together, most likely. And if you do, it's going to take you so long that it would have been better off if you just took the loss. Right? The second law of thermodynamics is always active. There was actually a rock group that made an album, and the title of the album reflects the second law of thermodynamics. Look at the title. Rust never sleeps. Do you get it? Things always fall apart. You can count on the second law of thermodynamics. That's why I'm bald. That's why there are little spots on my skin that weren't there a few years ago. That's why you have to clean the bathroom. Okay? Now this law is universally applicable. In fact, the first two laws are universally applicable. Now when we recognize that matter and energy are interchangeable, that's what I said earlier, E equals mc squared, these laws can be restated as follows. The total amount of mass energy in the universe is a constant. You can convert from mass to energy and energy to mass, but you can never change the total. All right? Secondly, the universe is undergoing a constant process of decay. And in this process, energy that's available to do useful work is going down. Order, in the form of structure and organization, is going down. And information that conveys meaning is going down. Right? These are all continually decreasing or decaying. Now, every scientist who is worth his salary acknowledges and relies upon these truths. You know they're true from your own experience. What are the implications of these for the origin of the universe? Okay, we're going to look at laws of process and the origin of the universe. Now, before I start this, let me just read a few words from Genesis chapter 1. In the beginning, God created the heavens and the earth. The earth was without form and void, and darkness was on the face of the deep, and the Spirit of God was hovering over the face of the waters. Then God said, "Let there be light," and there was light. Okay. In the next visual that I'm going to show you, we're going to be looking at how the second law of thermodynamics and the first law of thermodynamics tell us something about the universe. Okay? Now here on the y-axis, we have the available useful energy. That's this curve here. On this axis we have time. Going that way is forward. Now, this is where the universe starts. And right up here is 100% of the energy. At the very beginning, 100% of the energy is available for useful work. The universe is in its most organized state. Now, according to the second law of thermodynamics, the amount of energy available for useful work is constantly going down because as entropy goes up, disorder increases. And disorder makes less energy available for useful work. Now, anywhere along this curve, if you measure this distance and this distance, they add up to the same thing, right? Now, what's above here is energy that's no longer usable for useful work. And what's down here is energy that is still available for useful work. Now, the second law of thermodynamics says that this curve only goes in one direction. It only goes down. It never goes up. Now, I don't know if anybody has done a calculation, and the assumptions in the calculation would be difficult to get right. But it would be interesting to see if anybody's done a calculation just looking at the rate of increase of entropy in the universe to make a guess at how old the universe is. Okay, I don't know whether anybody's done that calculation, but you can see that wherever we are on this, it proves that the universe is not infinitely old, doesn't it? It proves that you can't go past this point. Right? Very interesting fact. Right? Now the first law, again, says that the total energy of the universe remains constant. The second law says the energy that's available to do useful work decreases with time. And so if the universe is eternal, well, that's not going to work, or very old, then it should have reached what scientists call heat death a long time ago. Now remember our example of the rechargeable fan in the box? When the battery in the rechargeable fan runs down all the way and it's not turning the fan anymore, and the air in the box has been heated up, everything in the box is going to come to the same temperature. There's not going to be any motion of any significance. Now there'll be random motion, the vibration of molecules, that's heat, but nothing useful. Okay? Once it gets there, that system has reached heat death. Now, do any of you like science fiction? Any of you ever read H.G. Wells? Okay, H.G. Wells' book, The Time Machine, has a chapter near the end of the book where the guy goes forward in time millions of years to where the Earth is reaching heat death. And he discovers that there's almost nothing moving on the Earth because everything is almost at the same temperature. It's not quite there, but he understood this concept. Okay? We're going to talk about the age of the Earth next week or the week following, by the way. This does not really prove anything about the age of the Earth except that the Earth and the universe can't be eternal. Okay? Now, we got a few minutes left, so let's push forward, see how far we get. Okay, let's talk about the Big Bang. All right? The Big Bang. Does it really explain the origin of everything? Or is it simply an attempt to explain a step in an assumed process that has led to the current condition of the universe while leaving the question of origin still unanswered? That's really what it is, isn't it? Now, the theory may be true. It may be accurate. It may help us to see back a certain distance in time, but it doesn't take us all the way to the beginning, and it doesn't explain origins. It only explains process. Okay? So if we go back to the uncaused cause problem, the Big Bang Theory is not a theory of cosmogony. Cosmogony is a theory of where the universe came from. It's a theory of cosmology. Cosmology is science that explains why the universe is the way it is now and the kinds of processes that have taken place in the universe. Okay? Now, there are some alternative theories that have been offered because many scientists have said, you know, you're right. The Big Bang doesn't explain the origin of the universe. Okay? Now, one theory is the theory of quantum fluctuations. Now, I got a note last week from one of you asking whether I was going to talk about quantum mechanics in this class. and I probably won't, partly because we won't have time, and partly because I'm not an expert on quantum mechanics. There may be a time to talk about it a little bit. Now, the theory of quantum fluctuations is a very interesting theory. Now, let me explain this law to you. Now, really, you'll be surprised. You can understand this. You can understand this. It's not that hard. Okay? According to the theory of quantum mechanics, the law of the conservation of energy can be violated for very short periods of time. In other words, in empty space, it is possible, for example, for a positron and an electron to come into existence next to each other very briefly and then go out of existence. Now, you know that a positron is an antimatter electron. If you mix two antimatter things which are a pair, they will annihilate, and what comes out is energy. Okay? Now, according to this equation, the amount of energy multiplied by the amount of time that energy can exist breaking the law of the conservation of energy is equal to a number called Planck's constant divided by 4 pi. Now, I did a rough calculation before class tonight, and I think I got it approximately right. Now, this is what the calculation said. In order for an electron and a positron to come into existence spontaneously, which is possible, how long could they exist before they go back out of existence? Well, according to my calculations, you take a billionth of a second, you take a billionth of one of those billionths, and then you take 9/10,000ths of one of those billionths of a billionth, and that's how long that electron pair can exist before it must go back out of existence. Now, I don't know the exact number of electrons in the universe. I think it's a number somewhere around 10 to the 80th. That's a 10 with 80 zeros behind it. It's a very, very big number. Now, if a single pair of an electron and positron can only last for 1/10,000th of a billionth of a second and come into existence spontaneously that way, then what's the likelihood that the entire universe came into existence spontaneously? And if it did, how long could it last? The numbers are absolutely absurd, right? The theory of quantum fluctuations is an attempt to use this idea of the temporary violation of conservation of mass and energy to say that the universe sort of just bounced into existence out of nothing. The theory doesn't work yet, and I don't think it ever will. Okay, now, there's another theory called the Big Crunch. Okay? Now, we said that the Big Bang is not a theory of origins, right? It only takes us back to the beginning. Well, the Big Crunch says this: there's a Big Bang and everything expands, then once it's all expanded, it's like there's a big rubber band pulling it back, and it goes back into the ball. And then it expands, and it goes out, and it goes back into the ball. And it just goes boing, boing, boing. Now, that's an attempt to get around the problem of origins. They say, well, the Big Bang wasn't the beginning. There was a crunch before that, and then there was a bang, and then there was a crunch, and then there was a bang. That doesn't solve anything either, does it? If there is an endless cycle of physical processes going back in time, that means the universe is its own self-existent cause. You still haven't escaped the uncaused cause. Okay? That's the theory of cyclic expansion and contraction. Now, here's a new one called steady state theory. This is one of the most popular ones now. Steady state theory says that the universe is full of something called dark matter. Now, dark matter is invisible, and you can't see it. That's kind of funny, isn't it? It's invisible, you can't see it, you can't measure it, but it's there. And dark matter has this very interesting property. When entropy increases in our universe, dark matter has entropy decreasing. So, entropy decreases over there as it increases here, and then after a while the whole thing reverses the process. It's just like this one, okay? It doesn't get you around the problem of an uncaused cause. Either the universe is its own uncaused cause, or something outside the universe is the uncaused cause of the universe, right? Now, it's very interesting. People tend to worship what they consider to be the uncaused cause. And many scientists sort of worship the physical world. They have a respect and an admiration for it. Now, that's not wrong necessarily, but the problem is they're worshiping the wrong thing. Romans chapter 1 says that when people suppress the knowledge of God and refuse to worship Him, they instead worship created things. And that's not just idolatry. That's not just idolatry. You know, I think I mentioned last week that I can't stand the voice of David Attenborough. David Attenborough is the guy who narrates all those nature programs. I just don't like the guy. There's something about him I don't like. But he's always talking about how evolution did this and evolution did that and nature did this and nature did that. And he's admiring it. It's great to admire it. We just admired the incubator bird, right? But I think for most of us in this room, when we admire the incubator bird, we're thinking the God who made that is pretty amazing. Okay? Well, we're out of time. Next week we will finish up this subject in a little bit, and then we're going to move on to evolution. Okay? Let's pray and let's go. Father, we thank you for the time that you've given us. We thank you for placing us in such an amazing world. Thank you that so many things work so well. That life goes on, that the sun comes up, that you provide us rain and food and shelter. Thank you for the amazing bodies that we live in, for the fact that they heal themselves so well. Thank you for the joy of living. Thank you most of all for revealing yourself in your word. Help us, Father, as we enjoy your good gifts, to give you thanks and worship. As we pray through Christ. Amen. Okay, see you next week.
Thanks for watching. If you have enjoyed or benefited from this study of science and the Bible, I hope you'll recommend it to others. Also, like and subscribe to my channel. See you in the next part of the series.